Now let us analyze the case of a system which is having unbalanced three-phase load. However, in the unbalanced three-phase star connected load, two of the impedances are equal. So there is some lesser difficulty or lesser involved equations in such a case. It is a very special case for a general case of totally unbalanced star connected load. Now let us see what is the easiness or ease which we can see or utilize in making various various sequence networks and their interconnections. Now we have seen that we can write VAA0 equals to ZS IA0 ZM1 ZM2 IA1 plus ZM1 IA2, and VAA-1 can be written as ZM1 IA0 plus ZS IA1 plus ZM2 IA2, VAA-2 ZM2 IA0 plus ZM1 IA1 plus ZS IA2. That we have already seen. Okay. Now we also know that in our special case which we are dealing, ZB is equal to ZC and there is a ZA in the third phase. Okay. Now we know that ZS is equal to ZA plus ZB plus ZC over 2. So it is equal to ZA plus 2ZB over 2. Similarly, ZM1 is equal to, sorry, it is 3 not 2, ZA plus A ZB plus A square ZC over 3 equals to, now ZB is equal to ZC. So it is equal to ZA plus A square ZB. Now this is equal to -1. So I will write it as ZA minus ZB by 3 equals to ZM1. And ZM2 is equal to same ZA minus ZB over 3. So ZM1 is equal to ZM2. So I will write it as ZM1 is equal to ZM2 is equal to Zm. Okay. Now I will put this in these three equations. So what are the equations which they become? VAA-0 equals to ZS IA0 plus ZM IA1 plus ZM IA2. Let us say this is equation number 1. VAA-1 ZM IA0 plus ZS IA1 plus ZM IA2. And the third equation we can write VAA-2 is equal to ZM IA0 plus ZM IA1 plus ZS IA2. Okay. Now with these three equations we can draw an equivalent sequence network interconnection. That let us see how to do that. Here there is a little less space. I will do that in the next slide so that all the three networks are shown here only. Now here I have again written all those three equations which we have seen in the previous slide. Now let us draw an interconnection of the various sequence network for this kind of system. Although for a general case we cannot draw independent sequence network because it is an unbalanced system. However, for this special case, when two impedances are equal, we can draw independent sequence network and their interconnection at the unbalance point, at the point of unbalance in the system. Now let us draw that. We can see that in this equation, each voltage drop, each component of the voltage drop is depending upon the self impedance and the mutual impedance. This self impedance is flowing in the current of the same sequence. However, the mutual impedance is present in the flow of the current of other sequence currents. Okay. So similarly, you can see 0, ZS0 and M is here for A1 and A2. Okay. So in this way, it is giving us a hint that if I make various sequence networks, this is the positive sequence network, A dash, VA dash, this is current IA1, this is current IA1, and let us draw the negative sequence here. This is the reference A dash, VA dash 2, this is current IA2, this is the reference for zero sequence A dash, this is voltage drop A dash 0, this is current IA0. Now we need to find that whether we can represent these three equations by interconnection of these three sequence networks. It can be represented if I add, you see, for VA dash only, it should have IA1 for the positive sequence ZS, IA1 should flow into ZS only. However, IA2 and IA0 should flow into ZM. Okay, so how to do that? It can be done if I take something in parallel. So you see that if I take something in parallel such that IA1 is flowing in ZS and IA2 and IA0 are flowing in ZM, so I can get VA-1. Let us say IA0 and IA2 are flowing in this, and I take these in parallel. So if I make a KVL loop here, it will be IA1 ZS plus IA0 ZM plus IA2 ZM. Okay. So this equation is now satisfied. Now let us proceed to the next equation. Now it should have IA2 ZS and plus IA0 ZM and IA1 ZM. So I will have to add IA1 also to satisfy this equation. Now if I add IA1, it will have a term IA1 ZM. So this thing will be destabilized now. So I will have to subtract IA1 out of it. If I do this thing, then again both of these equation, this equation and this equation are satisfied now. You can easily see that IA2 ZS plus IA0 ZM, IA2 ZM plus IA1 ZM. These two will get cancelled out, only this will remain. Similarly, I can now write the third equation and draw the equivalent circuit diagram. ZS minus ZM so you see that in this special case, when ZB and ZC are equal or two of the impedances are equal, I can make an interconnection of these sequence networks. However, whenever all of these are not equal or all are different, then we cannot make such an interconnection. I could have derived this network just by doing one thing, adding and subtracting so it would have given an equation ZS minus ZM IA0 plus IA0 plus IA1 plus IA2 into ZM. Okay, similarly I could have written it directly minus ZM IA1 plus ZM IA1. Then it would have directly given me equation ZS minus ZM IA1 plus ZM into IA0 plus IA1 plus IA2. So in this way, I could have derived this interconnection of sequence network from these equations just by subtracting and adding ZM IA0, ZM IA1 and ZM IA2. Okay, now we have got this interconnection. Now we will try to see one or two special cases from this same sequence in network interconnection that we will do here. Let us say this is the load ZA, this is ZC and this is ZC or ZB. Okay, now it is told that ZB is equal to ZC, so I will write it as ZB only. Now let us say that ZA is equal to infinity and ZB is equal to ZC is equal to ZF by 2. Okay, so what does it mean? It means that the network will change into like this. So you see, what does it mean? It means that it is a circuit equivalent to a line-to-line fault between phase B and C with ZF as fault impedance and phase A is open. Okay, now if I put these values in ZS and ZM values, what I will get? ZS is equal to 1 by 2 or 1 by 3 ZA plus 2 ZB ZM1 is equal to ZM2 is equal to ZM is equal to 1 by 3 ZA minus ZB. Okay, now From this we can find that Zs minus Zm equals to 1 by 3 Za plus 2Zb minus Za plus Zb, or equals to 1 by 3 into 3Zb equals to Zb. So Zs minus Zm is equal to Zb, and Zs is equal to 1 by 3 Za plus 2Zb. Now this is equal to infinity, so it is equal to infinity. And similarly Zm1 is equal to Zm2, and this is equal to infinity, so Zm is also equal to infinity. However, Zs minus Zm is equal to Zb. So let us see how the circuit changes now. This Zm is infinity, so it will be an open circuit now. However, Zs minus Zm is equal to Zb. So it is equal to Zb is equal to Zb is equal to Zb. Okay. This is Ia1, this is Ia2, this is Ia0. Okay, now you see that zero sequence current cannot flow now, because if they flow, they will flow here also. Okay, so this is kind of an open circuit now. Now what is the remaining equivalent circuit? You can see that it is equal to Zb plus Zb, equal, that is positive sequence network Va1 and negative sequence network Va2 are interconnected with a voltage or with an impedance twice of Zb. Now twice of Zb is equal to Zf. So it is equal to Zf, and it is Ia1 and it is Ia2. Now you see that this interconnection we have already seen for line to line fault in our one of the previous lectures when we studied the line to line fault in the three-phase system. Okay, so in this way we can derive various fault as a special case of this sequence network which we have studied in this lecture only. So no matter how difficult is the case, we can determine the equivalent connection of these sequence network to find various interconnection for various faults which we have studied in our previous lectures. So this is kind of culminates into all the studies which we have done in the form of symmetrical components. So if you find that this lecture is helpful to you, then please share and subscribe my YouTube channel. Thank you.